So for this one, what is the current in the wire of radius r equals to 3.4 millimeter if the magnitude of current density is given by JA, in which r is the radial distance and J0 is 5.5 times 10 to 4 ampere per meter squared. So actually, it's just a simple integration. Okay. So for this question, IA will be the integration of JA dA. Because the J has the same direction as the area vector, so we directly skip the dot product. And as I mentioned last time, dA can in the polar coordination, so we can rewrite it like this. And JA is J0 small r over capital R, and dA will be R dr d theta. So this is the area, and we change it into the polar coordinate. So we have R dr d theta. And R is from 0 to capital R. Theta is from 0 to 2 pi, which is the whole circle. So J0 and R are constant. So we have 0 to R squared dr. And also we have 0 to 2 pi d theta. So usually these questions are simple. So the variable usually is not related to the angle. So usually we just integrate from 0 to 2 pi. So which is 2 pi. And here we have J0 over R. And here we have R cubed over 3. This is 2 pi. So this is 2 pi R squared over 3 J0. So we substitute all the numbers into it. So this is 3 times 3.4. 3.4 times 10 to minus 3 squared over 3 times 5.5 times 10 to 4. So the answer is 1.33A. Any question in regards to this question? this one is a simple integration. So for the next one, the only difference is the current density is different. It is JB equals J0 times 1 minus small r over capital R. And well, J0 is also the same. And which function maximizes the current density near the y surface? So for this one, okay, for this one, this is quite similar. So IB is equals to JB dA. So similarly, we have integration from 0 to 2 pi, integration from 0 to R. And actually JB is J0, 1 minus small r over capital R. And dA will be R dr d theta. So similarly, J and capital R are constant. So we can factor it out, and we have 0 to R. Here, capital R minus R times R dr. And the second one will be 0 to 2 pi d theta. So in this case, we have J0 over capital R times R cube over 3 sorry, R cube over 2 R cube over 2 minus R cube over 3 times 2 pi. So it is pi r square J0 over 3, which is half of the previous answer. So for question C, what function maximize the current density near the wire? Of course, J is the answer. JA maximize J near the surface. No. Should be J. No, should be JB. Oh, JA, yes, JA maximize. So for question C, JA maximize. Because for JA is J0 small r over capital R. So when small r equals to capital R, JA is J0. But for this one, oops, okay. For this one, when small r equals to capital R, then this one is 1, 1 minus 1 is 0. So JB at capital R is 0. So which means JA maxima is the current density near the Y surface. So this is the last example. This is the last example for this chapter. Maybe I still need that one because I need to write manually. Okay. So for this one, wire section 1, so which is this part of diameter capital D1, which is 4R, and wire section 2, which is this part of diameter D, or this one should be D2. This should be D2. Okay. This one should be D2. So this should be D2. Connected by a taper section, the wire is copper and carried current. Assume that the current is uniform distributed across any cross section through the wire width. The electric potential change V along the length L equals to 2 meters, shown in section 2 is 10 mil V. So this part is 2 mil V, 10 mil V. The number of charge carried per unit volume is 8.4 times 10 to 28 per meters cube. What is the drift speed of the conduction electron in section 1? So first of all, we may calculate the electric field. The electric field at section 2, which is V over L. It means that, I see this point. It mentioned that the electric potential change V along the length L, which should be expressed like this. Which should be something like, if we choose this part and this part, the delta V here is 10 mil volt. Because you have a current going either way. And so due to this current, there will be some voltage drop or potential change. So we have 10 mV for length L. So we can calculate the electric field at section 2 is L is 2 meter. So E field is 5 mV per meter. So we know the Ohm's law in the field form, so we have something like this. Oh, sorry, this one is not sigma. This one should be rho. This one should be rho. Rho is the resistivity. Sigma is the conductivity. So we have 5 mu over rho is 1.6 times 10 to minus 8. So this is 296 A per meter square. So up till now it's not it is not difficult, and now it's mentioned that the current is uniform across any cross-section area, which means that as we calculate the cross-section here and here, the current should be the same, which means that we will have J1A1 equals to J2A2. So we will have J1 equals to J2 times A2 over A1. And J2 is 296. Area will be the area. This is a diameter, so the radius is half of it. So the radius for section 2 is R. The radius for section 1 is 2R. So diameter. This is a trap if it is appear in the exam or quiz. Oh, no. So here should be pi r squared. Here should be 4 pi r squared. So the current density at section 1 is 74 A over meter squared. So finally, we can calculate the drift velocity using J equals NEVD. So in the lecture, we have J equals NEVD. So we divide ND on both sides. So we have VD equals J1 over NE, and we have 47 over 8.49 times 10 to minus 28 plus 28. times 1.6 times 10 to minus 19. So the velocity is 5.44 times 10 to minus 9 meter per second.电场是 U 里。因为这里就是怎么说？因为这一边是一个uniform distribute across any cross section. So well, because for resistance, the voltage drop should be distributed uniformly, because it is only a material and the geometric are the same for different something like the x along the x-axis. So for this part, it is not uniform, and for that part is uniform again, but this uniform is not the same as that part.